Now I would like to make a little break in this direction, and I would like to discuss now the Langevin equation. Okay, so this approach has been the one used by a great physicist called Chandrasekhar, and this is summarized in his very classical and very important review, The Review of Modern Physics, in 1945. So I would like to discuss the Langevin equation, which is again the basis of using stochastic processes in biology to understand how particles are moving. So the Langevin equation. So basically we are interested in understanding how a bead, a particle, is moving, let's say, in a gas. Later on, if it's more dense, it can be called a fluid. But let's start with the gas. So you have a particle, x of t, and the question is how this particle is moving when it is responding to beads that are reflected. So you embed these into a gas of particle. The particles are moving. If nothing happens, it has some velocity, which we're going to describe in a second, the distribution of those velocities. It hit the particle, and then it is reflected according to the classical, let's say, Snell-Descartes reflection. The particle reflects. And so the question is, what's the motion of this bead? So now I'll give you the assumption about the medium, because it is important to understand this. Let's make an assumption that the medium is homogeneous. Homogeneous medium. For example, if we are close to a wall, might not be necessarily correct what I'm saying. Or if, for example, you have beads, heterogeneous beads of different sizes, for example, that will of different velocities with create some heterogeneities. What I'm going to say is not going to be true. So we need some kind of homogenization, that each force that hits the bead, they are all independent forces due to this collision. So when you have a jump in the velocity, this is like what? A difference in velocity. In the classical Newton's equation, this is like a force. All right, so I would like to have an assumption is all the forces here are all independent. This force is independent from this one because it is done by particles that have no relationship. So forces on the bead are independent. Right? And the fact that they are independent can be translated into the fact that in average there is the same quantity of collision from the left, from the right, from the top, from any plane. Right? So in average, so according to this description, the expectation when you average all of the forces exerted on the bead, it is 0. So this is how it translates. Okay, so now what was the idea? If you start, so let me recall the classical Newton's equation says that if you have a mass of a particle and the acceleration is directly connected to the force applied to the particle. This is Newton. Now we are back 300 years in time. So this is Newton's law of motion. And now we need another assumption, is that there is a drag force. That is, when the particles start to move with a deterministic speed in this ensemble, it will be stopped because of the particles that are colliding. And this drag force, we're going to assume, this is an assumption, that it is proportional to the velocity. So we have this drag force that you have in the fluid, which is proportional with a constant gamma velocity. There are models where you don't have just proportionality. It can be more complicated. It can be nonlinear. Okay, so then, which means that, so now let's assume I will not drive, I put the mass equals to 1, so the Newton's law of motion is like dv dt equals this drag force minus gamma f plus all the collision. So this is like a term that is the consequence on the velocity of the bead, plus the forces, which are the collision forces, right, that occurs on the beads in all directions. And I'm neglecting all kinds of other forces, electrostatic, gravitations. This is the basic approach.
Sorry, so what's the last form of the force?
Collision. This is the collision that I've described here.
Okay.
The collisions is the description of the force on the bead that are all independent. Okay, so we have this drag, we have this collision, and we said that according to this equation of motion of Newton's law, this is the what we have, and what we would like to do is to understand what is, can we say more specifically what are the collision if we assume that we have a gas of particles that are colliding, and then what is the probability to find the particle, let's say, here, at position y, at time t. How do we calculate this probability? Okay, this is a mission of 20 minutes that we are left. All right, and then you'll have time it will be time to rest. Okay, so now you embed this into a gas of particles. What is the description of the statistics of a gas of particle? What is the big name? The guy who committed suicide. That's right. You know the story of Boltzmann. Nobody believed what he said. Could not cope with all of this. So he killed himself. He was probably 10, 20 years advanced below his time. You know, he understood that the physics could be understood in terms of these collisions of particles, while everybody was thinking thermodynamics. Okay, so what Boltzmann said? He said that the probability, okay, let's first write the general concept. The probability that the particle will have a velocity, let's say, that belongs to the space of velocity, condition that, let's say, v0 equals v0. This can be written in the space of velocity as the probability to switch from v0 to v during it. So you integrate dv. This is the probability that you change from a certain velocity. You start at 0, let's say with a velocity v0. You ended up at time t with a certain set. So I'm not here in the space, real space, I'm in space of velocity. This is the real space. And so in here, you see, you can have the velocity. So you have the distribution of the possible velocity. You can do this, different direction. This is dv. Now, we know that this what is this? Let's look at this more closely. What's the probability distribution when t goes to 0 of this probability density function? If t goes to 0, the velocity should be equal to v0. So then we are left with, this is delta Dirac of v minus v0. What is the limit of pt of v and v0 when t goes to infinity? I go to the other direction now. It should, the particle, you wait, so it should be embedded into all of these particles that collide all the time. And what, how do you characterize this? Now you need to look at the statistical properties of the ensemble. If you wait sufficiently long enough, so you lose track of the particle. And the particle, even if you pushed very strongly, at some point the initial push of the particle should not be important compared to all the collisions. So the memory of the initial kick should be forgotten. Yeah, this is the classical statistical physics. And then what's the distribution of velocity? It is
one divided
I'm sorry.
1 divided.
One.
No,
The velocity. What's the Boltzmann said? The Boltzmann said that it should be distributed according to the Boltzmann distribution. You've seen that in the past? So what's the Boltzmann distribution? It's simply the exponential. I mean, there is a factor here. So this is, if we're in dimension 3, this is associated map with the dimension. I'm not going to live in dimension 4 or 5, right? People interested in biology. And dimension 3 is good, and dimension 2 and 3 are important because what happened on the membrane. And we'll see dimension 2, there is specific behavior. Okay, I'll do it in dimension 3. So this is m divided by 2 pi k b k Boltzmann t. So this is where the t here, temperature, connect to the statistical property of our ensemble to the power 3/2 exponential of minus mv squared. I think there is a 2 here, which is missing here. 2 kbt. kbt. M is the mass, so here it's m equals 1. So sometimes I write m equals 1, sometimes I leave it m. V, this is velocities, so they are distributed. So this is a distribution, a function of v. So the probability, if you are interested in this quantity, we have to plug this into here, and we get this quantity. But the idea, it's important to understand here. We are connecting here the motion individual particle to statistical quantity, the temperature. Temperature is the key. You know, that's a statistical quantity. This is a quantity that represents the behavior of an ensemble. Okay, so now I'm going to connect quantity, which is represent an ensemble, with behavior of a single particle. That is, out of all of this, you look at one of them. Okay, so now let's start to do the, so now we have this is the behavior, assuming that we have this behavior of Boltzmann, right? We have a bath of thermalized bath. If there is a gradient of temperature, this is wrong, because gradient of temperature means that you don't have a uniform temperature. Assume temperature is fixed. Now, I would like to get information about the collision term and how this collision term can be expressed in more specifically. We know that there are independent particles, so the expectation according to the statistics here is 0. And now to get more inside, we're going just to integrate this equation. How do we integrate this? So all of this part that I'm going through here, I think corresponds to the 61st pages of the book of Schuss, plus the article of Chandrasekhar of 1945. I mean, this is taken from there. Why? Because this is very good. The presentation and the ideas putting together was he did a very great job on this. So, how do you integrate this equation? You multiply everything by exponential gamma t, v, and if you differentiate this with respect to time, this is equal to exponential gamma t multiplied by v dot, plus gamma v, right? And this equal to this, so this is this plus this equals to f collision, which depends on the time, exponential gamma t. So now we can integrate this the way we have discussed the integration. So this is exponential gamma t v of t minus what happened at 0. So this is 0, this is minus v of 0. And this is the integral from 0 to t of f collision s exponential gamma s ds. Okay, so now let's understand. I multiply now everything by exponential minus gamma t, so I multiply here by exponential minus gamma t, so I remove it from here, and I add it here, exponential gamma t is minus. So what is the limit of this term when t goes to infinity? This is by definition, this is v0, this is finite, exponential gamma t, d goes to infinity, goes to 0, right? So basically this is what we said after some times, v of t, the velocities, only depends on the collision term multiplied by a kernel, which is exponential gamma s minus t. This is an important kernel, it's called the kernel here associated to the lack of the initial velocity. All right? So now, so this is what we have. Now, how can we calculate this term? If those are random variables, independently distributed, and so the idea is that they are falling exactly into the set of non-anticipating function, which was just written over here. That is, what happened here doesn't depend on what happened in the future, on this increment of omega t plus s minus omega t. So let's write it this way. Suppose we go from 0 to t, and we chop it into pieces. Then we get in here, this is sum of exponential minus gamma t plus gamma k delta t, f of k delta t multiplied by delta t. So I discretize this integral. This is sum over k, and I assume that each part here is on the same beam, which is a fixed delta t. And you integrate from 1 to n. Now, I'm going to set this framework, saying that finally, if we have independent, if you get this independent sum of collisions, you can write it, this is d omega k equals f of k delta t multiplied by delta t. So I call all of this term d omega k. By definition, we say that f of k delta t, because this is independent, the expectation of this is 0. So, and then, since we have a sum of collisions, f represents a sum of collision, we know that a sum, so there is maybe a theorem here of large number to invoke, is that the sum of independently distributed variable converges, whatever the sense of converging here, to a Gaussian a process when the mean is 0. And so what we can write here is that d omega k is a Brownian motion with a diffusion term, which I'm going to call 2q delta t. We know that d omega k can always be written this way. And q here is unknown. And I would like to define and to understand what q is. Okay, and so for this, what we need is to link what we said before, the motion of a particle with the velocity. And so we need, what is the, we can calculate from this distribution, we can calculate the mean velocity. And we can calculate from this also the mean velocity. because, I mean, the mean squared velocity, because the mean here, as we are going to see, is what? Is 0, because it doesn't move in average. But so that's why we need to calculate V squared, expectation of this. What is this equal to? So remember, we're in dimension 3, so there is x, y, and z. So I usually make a lot of this like here, x, y, and z, and they are all independent. X is independent of y, independent of z, so it's 3 times basically in x. So this is 3 times the expectation, let's say, if you are only in one direction. So we can just go back to dimension 1. So this, how do you calculate this? This is calculated from here, because you can calculate at equilibrium when t goes to infinity. So I'm interested in calculating this term, the limit when t goes to infinity of the expectation of this, which is 3 times the expectation of 3 times the limit when t goes to infinity of this. And now I would like to calculate this using this infinite probability density function. So this is just v squared p infinity of v, which is independent of the initial position. And then we have to integrate over the space of velocity in dimension 3. So this will give you the result. This you can calculate, you multiply v, you integrate over a ball in R3. This is elementary calculations. And you end up with a Gaussian integral, you integrate by parts, right? And you get 3 kBt divided by m. Okay, so this is one calculation. Again, this is integrated over R3, because velocity lives in R3. And the 3 comes from here, and yeah, I don't know why I did this reduction, but okay, this is the result. Now, there is another way to calculate v, is to use this integral. So vt equals v0 exponential minus gamma t, plus integration from 0 to t of f collision of s exponential of gamma of minus t minus s ds squared. So I do this. Square. So square, okay, let me do all the calculation now. So this is squared plus twice v0 exponential minus gamma t plus integration from 0 to t of f of s exponential minus gamma t minus s squared. Okay, and now I take the expectation of everything. Expectation of this is 1, because there's no, everything is deterministic here. So here we ended up with having 2, expectation of all of this, plus the expectation of this. So now we're interested in taking the limit when t goes to infinity of all of this. So I'll take another limit here when t goes to infinity. What is the limit when t goes to infinity of this term? 0, because exponential, this is 0. What is the expectation of this term? 0, because expectation of the integral is the expectation of this term, and this is deterministic, and the expectation of s by definition, it was written, yeah, it's still there, it is 0. So this is everything is 0. Now what we need is to calculate the limit when t goes to infinity of this integral. Okay? 5 more minutes and we are done. And so this you can do the same way as we did before. This is the integral, so we can slice it. I'll do it one more time. I sliced f of s between 0 and t, so that this integral is f of k delta t exponential minus gamma t plus gamma k delta t. And then we have to make it square, right? So square is the sum for k and q of f of q delta t multiplied by this, multiplied by exponential gamma t plus gamma q delta t. So this, all of this term is equal to this one. This is equal to this. You agree? I didn't make any mistake. And so, yeah, so clearly the gamma 2, and so we have exponential gamma, this is the same term. If I take the expectation, this is the deterministic term. This, by definition, when I take the expectation, everything will be 0 because we have f, and I have forgotten here delta, I have delta t twice, right? No. D omega, yeah, I have d, yeah, that's it. No, this is delta t twice. Delta t twice, but f delta t, since f delta t is d omega k here, so I put one delta t in here, another delta t in here, and this is d omega k, d omega q, exponential 2 gamma t, exponential gamma k delta t plus gamma q delta t, and the expectation of this k and q. And now this is 0 by definition, except when k equals q. So I can put it here, square, k equals q. K equals q, which means here twice. And this is simply, this is simply tk plus 1, delta t, sum, okay, exponential minus 2 gamma t, exponential 2 gamma k delta t. And this, when t goes to, delta t goes to 0 and k goes to infinity, there is here factor 2. This is exponential minus 2 gamma t, integration from 0 to t of exponential 2 gamma s ds. All right, and this can be integrated into exponential minus 2 gamma t, exponential 2 gamma t minus 1 divided by 2 gamma. Now we're almost there. When t goes to infinity, this multiplied by this is exactly 1. This multiplied by this goes to 0, and we get 1 divided by 2 gamma.
I think we lost the q somewhere.
What?
We lost the q.
We lost the q? Yeah, that's true. We lost the q, that's very good. So it's 2q, yeah. So this is here, we have, I forgot 2q here. Because expectation of this is 2q delta t. So we have 2q delta t, thanks. And so here we have 2q divided by 2q. So 2 and 2 goes. And this calculation is almost, yeah, no, this is correct for a velocity which lives in dimension 1. Because here this is for, let's say, v of x. So we ended up here having q divided by gamma. So now we have, from one shot, where it's written, yes, this is 3 kBt divided by m, and here we'll have, this is only for dimension 1, I did it, on 1 dimension, so if we're in 3 dimension, I did x, y, and z, so it's 3 times q divided by gamma, so this is the final result. 3q divided by gamma, which is the result of all of this calculation coming from the limit of this. 3 times this, because x, y, and z, should be equal to 3 times kBt divided by m. 3 and 3 goes away. So Q is equal to KB T divided by M multiplied by gamma. And finally, let's write back the equation that we had here before. We had dv dt, so M or V dot plus gamma V equals F. Now we have F, which is d omega divided by dt. So this is d omega divided by dt, which I put the limit, I'll call it omega dot. Omega dot has a variance 2q. So let's, if now this omega has a variance 1, what do I need here as a, so I want not to write it something with variance 1. It's another Brownian motion. What do I need to pull out from this? Square root. That's right, square root of 2q. What is square root of 2q? This is square root of 2 multiplied by q. What is q equal to? This is kb t divided by 2 kb t gamma. I don't know why there is m here. Yeah, okay, there is m because there is no more m here. Okay, let me do m equals 1. So because this is for my kbt. So here, this is very important what you are seeing here, because this is this is the form of what is called the fluctuation-dissipation, and then I have to stop in a second, of the fluctuation-dissipation theorem. This is very important, because this is the basis of many analysis of single particle trajectory, that you have the gamma here, the viscosity, and here we have square root of gamma. Square root of gamma. So this, the fact that you have gamma here and square root of gamma, this is called this is the essence of fluctuation dissipation theorem that we have reproved here using all of this analysis, like that if you have a particle, if this particle is living in an equilibrium ensemble of particles, then if you use this Boltzmann as we did, we connected the behavior of the ensemble to the behavior of a single particle, and then necessarily we found this relationship. If you don't have the fluctuation dissipation theorem, then you don't have necessarily this distribution. That's why when you are going to analyze data on the surface of molecule moving on the surface of the cell, if there is some coarse graining, for example, there is additional effect, for example, you have obstacles that remove the homogeneity, you should not look something of this type. You should look at something more general, is drift plus noise. Okay, in general, if you look at stochastic equation, they do not share this. They are written in general, drift plus noise. Only when you have embedded with the physics, you have this connection. Am I clear? Okay. Next week, you'll tell me if I'm going too fast, if it's too slow, if it's too elementary, or if it's okay. If it's okay, I'll move like this to make sure that you got all the steps before I go to the nice stuff connecting to biology. Okay? Now I have to rush.